To determine whether a matrix is invertible, we actually had to go about the process of computing its inverse. So our goal in this video is to develop a tool which will tell us whether or not a matrix is invertible without having to actually compute the inverse. However, we won't relate that tool, the determinant, to invertibility quite yet, so our objective here is just going to be to develop it. Now the determinant is built inductively, so we start with the easiest case. If A is a 1-by-1 matrix, so basically just a real number, then its determinant is just itself. To talk about determinants of larger matrices, we need to define a few new objects. So if A is an n-by-n matrix, and we'll only be looking at square matrices for this video, then if you give me any I in J, we define the ij submatrix of A to be the n-1 by n-1 matrix we obtain by deleting the ith row and jth column of A. So to see this in action, let's write down a random 4x4 matrix, and let's find its, say, 2, 3 submatrix. Now I'm really just writing down random numbers here. If you want to make an example yourself, the numbers don't matter at all. So since we want the 2, 3 submatrix, we're going to delete the second row and the third column like this. And what's left over makes up a 3x3 matrix, and that's what the 2, 3 submatrix of A is going to be. So next thing we're going to do is we're going to define a cofactor. Now we use the same setup as the submatrix definition, a square n-by-n matrix and a choice of row and column, in which case the ij cofactor is the signed determinant of the ij submatrix. Now hold on, there's a problem here, right? We don't know how to define the determinant of anything other than a 1-by-1 matrix. And I know that. The problem is that our definition of the determinant uses cofactors, and our definition of the cofactor uses determinants. So let me also give you the definition of the determinant while we're at it. If A is an n-by-n matrix, then its determinant is the weighted sum of its cofactors along any row or column. Okay, so let me show you what I mean by this. So suppose we have our big generic matrix like so. Okay, so let's say we take a look at the weighted sum over the first row. So we're going to multiply the ij cofactor by the ij element of the matrix, and then add them all together. So over the first row, that's what this is. And if we instead did it over the second column, we still weight the ij cofactor by the ij element of the matrix, and in that case we would get this. So in the 2x2 case, if we do this procedure, we actually get a nice formula for the determinant. So let's let A be the generic 2x2 matrix. And we can use any row or column to do this, so I'm just going to choose the first row. And I'm going to expand out the determinant calculation here in painful detail so that we are comfortable with the calculation, but you don't have to do this much work in general. And now think about what the M11 submatrix looks like here. If we delete the first row and first column, we're just left with the 1-by-1 matrix D. And the same is true for the 1-2 submatrix. All that we're left with is C. So the determinant of each of these 1-by-1 matrices is just its entry, and that gives us AD minus BC for the determinant of a 2-by-2 matrix. If we wanted to see this in action with numbers, we could just write down a random 2-by-2 matrix and compute its determinant like so. Now if you like, you could do something similar for a 3-by-3 matrix and so on for bigger dimensions, but the resulting formula is really quite messy. It's not worth memorizing. So I've done the calculation ahead of time and we'll show you the result just to demonstrate why it's not worth memorizing. And instead, I'm going to say that you should just repeat the cofactor expansion each time. Okay, so here you can see how messy this is. Chances are you'd get one of the signs wrong or you'd make a mistake in the order and your answer would be wrong. So like I said, when you're computing a determinant, just repeat the cofactor expansion. So here's a 3-by-3 matrix. Let's work out its determinant. And before starting, let's think about which row or column to expand along. Since we multiply each cofactor with an element of the matrix, it makes sense to choose a row or column with lots of zeros. So in this case, column 1, column 2, row 1, row 2, any of those would be a good choice. Now I'm going to go with row 1 here. I suggest you pause the video and try the expansion along a different row or column. This will just give you some practice doing your cofactor expansion, but it's also going to help convince you that you get the same answer regardless of which row or column you use. So again, I'm going to write this out in painful detail. And as you practice more, you'll be able to go straight to the submatrix computation, but let's make sure that we're comfortable with how this works before we start taking shortcuts. Okay, so we know how to compute everything here. For the most part, we're just reading off the matrix. Okay, and even though this middle term is going to become 0, I'm going to fill in all the details here so you can see how it would have been done if it weren't 0. And we can just read off the determinants of each of these 2x2 matrices, giving us -2 as our final answer. Okay, and again, make sure you try this calculation over a different row or column, both for practice and to see that you get the same result.